So maybe we get started. Can everybody hear me? Okay, so today we'll be talking about robustness of deep neural networks. So this is today is going to be more advanced topics where we'll be seeing robustness of deep neural networks, which is a very, very hot topic nowadays in research of deep neural networks. And we'll also be seeing reinforcement learning taught by Jalal, which is also something that is quite advanced and really topic of many research papers. So you've seen that with machine learning you can do really many, many different things that are just awesome. Like you can classify very complex images and very complex labels. You can do speech recognition. You can play complex games like the game of Go and the game of StarCraft and so on. You can automatically generate captions of images using recurrent neural networks and so on. This is really especially in the case of image classification, you've seen huge improvements in the last few years using deep neural networks, where this is, for example, the error rate that you achieve on ImageNet, where you go from 25% error rate to less than 5% error rate in 2015, which is on par with what the human is actually able to do on this task. So this is really something that we've been experiencing in the last few years, and I hope that throughout this summer school, you really saw the power of machine learning in achieving such tasks. Now, the question is, are we ready to deploy these things in real world and in autonomous cars and so on and so forth? Now, if we want to make sure that these things will not break, we need to basically certify that the machine learning systems that we've developed satisfy some constraints. In particular, the constraint that we'll be looking at today, which is something fundamental, is the robustness. So what do I mean by robustness? Basically, if you have the image, let's say that is classified as a lampshade by this image, by this classifier, by a state-of-the-art neural network, for example, and you perturb this image just a little bit. Here, for example, you have a geometric transformation, okay? And you input this to the classifier. You also want the output of the classifier to be a lampshade, okay? So you do some perturbation, okay, and we'll be seeing several of these perturbations, and you want the output of the perturbed image to be the same as the output of the original image. So we can really talk about many different kinds of perturbations. In particular, what we'll be talking about today is adversarial perturbations. So in adversarial perturbations, you have a malicious agent that tries to add the minimum amount of noise on your image in such a way to cause data misclassification. Okay? So it's really someone who is trying to fool your model in such a way to basically break your classifier. We'll also be talking quickly about random noise. So what is the robustness of your classifier to random noise? If you add random noise to your image, are you is it classified in the same way as the original image or not? And we'll also be quickly talking about geometric transformations, such as the one here. That's something things can be a bit more also realistic in the sense that you can change illumination, you can add occlusions, and so on and so forth. So really, if we want to deploy these things in real-world environments, we need to make sure that the classifiers are robust to such changes in the data. I mean, the data is not always clean in this way, right? So that's the topic of today. So before going into the main subject, I'd like to highlight why I'm actually interested in this topic. So I've been working on this for 5 or 6 years, and I think there are two main motivations why actually studying the robustness of deep neural networks is interesting. The first one is basically from a safety perspective. So say that you have an autonomous car here, and that you add some perturbation on top of the camera that is used to basically classify whether a stop sign is really a stop, whether something is a stop sign, whether something is a pedestrian, and so on. So if this kind of noise that you add, let's say as a sticker, on on top of your camera fools the classifier of this car in such a way that it changes the label of stop sign to like continue, or like from pedestrian to a car, or from pedestrian to a clear way, or something like that, then this is really, really problematic, right? So you can, for example, this will change the actions that the car will take. Like, for example, instead of thinking that overtaking is dangerous, we're just thinking that overtaking is fine, and it might lead to accidents and therefore really problematic consequences. So from a safety perspective, studying the robustness of deep neural networks is something that is really fundamental. But there is also another component to this, which is the fact that the robustness of deep neural networks has really like connections with our fundamental understanding of how the deep neural networks create decision boundaries and so on. So we'll be seeing today like some connections between the robustness of deep neural networks and the geometry of the classifiers, how the decision boundaries look like, the curvature of the decision boundaries, and so on. And so studying the robustness helps us to understand deep neural networks, and this is something I think that is really lacking in this field in terms of like our understanding and so on. So I think working on robustness allows us to increase this understanding. So the outline of the talk today is going to be like as follows. So you have a network, like the first part is going to be like you have a network, and then you want to assess how robust is it, how to do this. Okay? So in other words, how robust is your network of perturbations? How can you fool your network? Okay? Now, after this part, we'll be seeing basically how can you defend against attacks. Okay? So how can you make your network more robust? And then the last part is going to be more theoretical. We'll try to understand basically some of the connections between robustness and geometry, and derive some theoretical guarantees on the robustness that you can have on your network. Okay. So the talk is going to be like in the beginning, it's going to be like more practical and so on, and as it goes more and more, it's going to increase in difficulty and like be a bit more theoretical. Okay. Yeah, so part one, how to fool your network. So one of the really landmark results in the last few years is that state-of-the-art deep neural networks are extremely vulnerable to adversarial perturbations. So they might work extremely well, but they are extremely vulnerable to what we call adversarial perturbations. So what does this mean? Well, this means that this is recognized by a state-of-the-art deep neural network as a school bus. Okay? While this is recognized by the same state-of-the-art deep neural network as an ostrich. Okay? So you might not see any difference between these two images, and you're completely right. You're not seeing any difference, except that you have added a very small perturbation here to the left image in such a way to result to the right image. Okay? But this perturbation is extremely small, and the network is extremely sensitive to such perturbation, and therefore it completely misclassifies it. So this is really worrying because we don't see at all this perturbation in this image here, yet it completely misclassifies the deep neural network. Okay? So I'd like to emphasize here that this perturbation that I have found is actually an optimized perturbation. It's not like a random noise that I've added on this image in such a way to it's not just a random noise or something like that. This is really something that I have optimized for. I tried really to fool the classifier by solving an optimization problem. Okay? So for example, in this case, I have tried to find the perturbation with minimum L2 norm. Okay, this perturbation, I tried to find perturbation with minimum norm in such a way that when I add it to this image here, it results in misclassification. Okay, so we are very, very far from the regime of random noise, for example. Okay, so like more pictorially, what does this actually correspond to? So say that you have two classes here, like this is class 1 and this is class -1. Okay, and this is the decision boundary between these two classes. Okay, so everything here, all the data points here are classified as class 1, all the data points here are classified as class -1. Okay, and the robustness to adversarial perturbation is basically this vector here. here, or like the norm of this vector. Okay, so let's try to quantify this a bit. So what I call robustness to adversarial perturbation is given a data point x here. Let's try to find basically the minimum perturbation. Okay, let's say here in M2 norm. So that's the perturbation in such a way that my classifier, which I call k hat, okay, when you evaluate the classifier on the perturbed image x plus r, it is different than the classifier evaluating x. Okay. So this gives me this perturbation here, and the norm of this perturbation is what we call the robustness of the perturbation. Okay. So this is really a pointwise property. So this is really the robustness of the perturbation at x. Okay. So how can we really have a robustness of a classifier? Okay. So you can do this by basically taking the expectation over all your data points. Okay. And then you get basically a number that quantifies how robust is your classifier to adversarial perturbations. Is it clear? So the first thing we'll look at is how can you actually solve this problem. Okay, so you have a classifier, and then you want to see how robust is it. So in order to see how robust is it to adversarial perturbations, you really need to solve this optimization problem, correct? And this optimization problem is rather complex because like it involves the classifier as a constraint. So I don't think Hamza talked too much about constraint optimization problems. So here you have really a constraint, and this constraint involves a deep neural network, and therefore it's not a complex constraint. And so you need to kind of like have some heuristic solutions in order to find this like the optimum, or like tend to the optimum of this optimization problem. So there are many ways of doing this, but one simple idea is actually that works very well is actually to iteratively linearize the decision boundaries. So what you have here, so let's say you have this data point x0, and remember that our goal is to find the minimum perturbation that goes outside of this region here. Okay, so the decision boundary is non-linear because your deep neural network is generally going to create non-linear decision boundaries. And you really want to find the vector that goes outside of this classification engine here. Okay? So what you're going to do is basically you're going to linearize your classifier around x0, okay, which will result in a new classifier which have new decision boundaries, and these are the decision boundaries of the linear classifier. This is the decision boundaries of the new classifier that is linearized around x0. Okay, so now if you have a linear classifier, it's actually very easy to compute the distance or the vector that goes from this x0 to outside the decision boundary of this linearized classifier. This you can solve it in closed form. Okay, and this corresponds to this vector here that goes from x0 to x1, which you can compute in closed form. And so you can update basically your current data point to be x1 now, and then you linearize again your classifier around x1, and then you compute again this data point, this perturbation that goes outside of the linearized classifier, and so on and so forth, till you basically get a vector, till you get a perturbation that goes outside the original decision boundary. Okay? Now, this is not guaranteed to converge or anything, so this doesn't have any guarantees. However, in practice, we find that this is a very efficient technique in order to find this perturbation that goes outside the decision boundary, and therefore find a minimal perturbation that fools the classifier. Okay? So in practice, you really need like 2 or 3 iterations max in order to find a very, very small perturbation that goes outside the decision boundary. In other words, in order to find really this perturbation here that I showed you here. Okay? Now, this is just one technique amongst many different techniques that you can use in order to fool your classifier, and there's been like tons of approaches that give you this vector that misclassify. So people have created these like benchmarks where, so that's the approach that I talked about is called deep fool, and people have created benchmarks in order to, like evaluate different classifiers against the different benchmarks and so on. Okay, so this is one technique, this is another technique, and so on and so forth. Okay, but the thing to remember here is that it's quite easy to fool your classifier with a very simple gradient-based method that finds this perturbation that goes outside your decision boundary of your deep neural network. Okay, which was a very surprising, by the way, result a few years ago, because like these deep neural networks generalize extremely well, they work extremely well, they have very good performance, yet they are extremely brittle to very small perturbations that we as humans actually think should be quite easy to classify. Okay, is this clear? The adversarial perturbation? Okay, so in the recent years, like there's been this increasing number of papers on showing that actually you can find much more surprising things than even adversarial perturbations. So adversarial perturbations are point specific. So for each x, you have a vector, and this vector basically depends on x, right? So this perturbation, remember here, depends entirely on your x or on your image, your initial image, obviously. So if you change your image, you change the perturbation. This is very specific to this data point here. So what was shown is that there actually exists universal perturbations. So this basically means that there exists this unique image, which is this pattern here, in such a way that you add this to an image of a joystick, for example, and you get an image that is very close to the original image of the joystick, okay? So visually very, very close, yet is misclassified by the deep neural network as a chihuahua. Okay, and you add this same universal perturbation to an image of a flagpole, and then it is again like visually very similar to the original image, yet it is again something completely different. And then you add this image to a balloon, and then again it's completely different. And this is not something specific to these three images. It is it works for most images that you actually take with your cell phone. Okay, so this universal perturbation is kind of universal because it applies to any image, whereas the previous perturbation regime I was discussing is something that is specific to the image that you are considering X. Okay? So this was really kind of like a surprise, because this very simple pattern, you add it to any image, and it basically breaks your classifier completely. So from like 90% classification accuracy, you just get down to 0% or something, or like very close to 0%. Yet visually, it is very, very similar to what we, I mean, it is actually very trivial to classify ourselves as humans. So, how do you actually compute such universal perturbations? Okay, so geometrically, the universal perturbation corresponds basically to finding a vector that goes outside of many different classification regions. Okay, so let's say you have three classification regions. This is one. This is the second one, and this is the third one. And you have the different data points here associated to them, x1, x2, and x3. And then the goal is basically to find a vector that goes outside of all these. Okay? The same vector again. That's the universal part of it. So now, to simplify a bit my explanation, I'm actually going to do a simple transformation where all the classification regions are on top of each other. Or like I just have the data points here on top of each other. And so, like with this simple, this is by the way just for exposition. And so when I have this simple transformation, the goal now is to find a vector that goes outside of the union of all these three classification regions, right? Okay. So what I'm going to do is actually very simple. I'm going to start by finding a vector that goes outside of my first classification region. Okay. So I'm going to find here a vector, this vector here that goes outside of my first classification region. But then I'm going to notice that here, this data point is going to be correctly classified by 2 and 3, but not by 1. So it's not a universal adversarial perturbation. So I'm going to add, basically what I'm going to do is to add an increment to this vector in such a way, basically to lead to a second, to a misclassification for the second data point. classified by 1 and 2, but not by 3. Okay? So I'm going to add again a third vector in such a way to find like a vector, to have basically a point that is outside of the union of all these 3 classification regions. And now my final vector, which is basically the sum of all these, is going to be something that lies outside of the union of all these classification regions. Okay? So like the idea is very simple, it's just to proceed sequentially, and each time I'm not fooled by the current image, I'm basically going to add a perturbation in such a way to be fooled by it. Okay? And then I'm going to aggregate all these perturbations in such a way to get something that is outside of the union of all these regions. So if you write this in pseudocode, this is basically what you get. So you're going to loop basically on all the data points, okay? And then you're going to, so V is basically your universal perturbation, and you're going to check that if V does not fool the data point xi, then what I'm going to do basically is to compute this perturbation increment that I was talking about, this delta V, in such a way to cause data misclassification. In such a way that if I add this R, so I'm searching for this R, so in such a way that if I add this R to V, I get basically misclassification. Okay? So this is delta V, and then I'm going to make sure that V plus delta V, so my new perturbation is sufficiently smooth. So in order to do this, I'm going to project V plus delta V on the LP ball of some radius psi. Okay? So this we can solve using the deep pool algorithm I just talked about, which is finding adversarial perturbations, right? Because like this is just the same form exactly as what I talked about like a few slides ago. Okay, computing adversarial perturbations, and this is just a projection on a ball, so it's also quite simple to do. So the goal of this is to make sure that the perturbation, the final perturbation I get, is something that is sufficiently small and is something that is imperceptible. Because if I don't do this projection, the norm of my perturbation is going to get larger and larger and larger, and it's going to be extremely perceptible. Okay, so this like has the effect of projecting each time on the LP ball in such a way that it's imperceptible. Okay.
But in reality, I don't know if my data are perturbed or not.
Yes.
Here we start with an data who is not perturbed, and I added nosy.
Yes. So the goal here is the goal here is not to detect whether an image is perturbed or not. The goal here is really to find to show that deep neural networks are not robust to universal perturbations. Yes. Okay, and then we'll get to basically defenses later. Okay, but here it's like it's a proof exactly that you can basically find these universal perturbations. Okay, so basically we can train this universal perturbation on like 10,000 trained images from ImageNet, and then we set psi to guarantee this quasi-imperceptibility. So we set it to be 10/255 with the L infinity norm. And then the very important thing here is that we evaluate the perturbation V on the validation set. Okay? So all these images that I've shown in the beginning, with like the image of a balloon and so on, are not images that were used to train this perturbation V. Okay? These are images that are taken outside this set. Okay? And then the really surprising thing that we got here is that on the validation set, you actually get very high fooling rate, in the sense that when you compute this perturbation on this training set, you actually still fool most of the images that you get on the validation set. Okay? Even though these images were not at all in the training set. So in other words, actually we did this demo where we take pictures with your cell phone camera, and then these pictures are very well recognized by a standard classifier, but then you add this very simple mask on it, and then it basically fools all the images. So concretely, this is recognized by the deep neural network as an Indian elephant. So this was correctly recognized in the beginning as a Christmas stocking, but we have added this very simple universal perturbation, and it led to an Indian elephant. Now, we have added the same exact perturbation on this image here, which was correctly recognized before the adding the perturbation as a, I don't know, some sort of, I think Bouvier de France, which is some sort of dog. And now it's recognized as a wool. And the same perturbation was added, and then Indian elephant again, same perturbation added the African grey, same perturbations added for all the different images, and you see that all these images are completely misclassified. And these images, by the way, I have added, like I have taken myself, like with my cell phone camera, okay? And then again, this is completely wrong here, okay? But this is not something that is like specific to the ImageNet data set or something like that. It's something really that generalizes for most images. So what do these perturbations look like? So we can compute, we can basically visualize these universal perturbations for different deep neural networks. So all these things are like state-of-the-art deep neural networks, or were state-of-the-art deep neural networks. And if you look here, actually you get very structured perturbations, like very structured textures and so on. We don't have a very good understanding of why these kind of like magical perturbations fool the deep neural network. So it's still an open problem. Why these are these kind of like structured and textured images are really breaking the classifier. But the interesting thing here is that they have a very similar structure, and that's actually if you train your universal perturbation, let's say on GoogleNet, and then you try it on ResNet, for example, it's going to transfer very well. In the sense that it's actually doubly universal. So you don't even need to know what network you're going to try to fool. So you can train your universal perturbation on a completely different network, and then you test it on the network that you're actually trying to fool, and it's still going to work quite well. In the sense that the fooling rates that you're going to get are actually quite large. Okay? So by doubly universal, I mean a universal across the different images and universal across the different networks. Okay. Clear? Okay, so some people might argue that addition operation is not something very natural to images, for example. So you can think about other types of transformations, like for example geometric transformations, and then again have the same approach of like trying to find this minimal perturbation that you add to the minimal transformation that you apply on an image in order to cause data misclassification. And transformation here can be location, translation, scaling, shearing, and so on. Okay, so you can formalize it in the same way by basically trying to find here the minimum transformation. So here, for example, let's say T is the set of affine transformations. Big T is the set of affine transformations. So here, what you're trying to find is the minimum transformation from the identity transformation to tau. Okay, in such a way, again, same thing, that the classifier evaluated at x tau. So when you apply the transformation tau to x, it's basically different than evaluated at x again. And again, if you actually do the same kind of approaches, the interesting thing is that even though this thing is very low dimensional, okay, this T is very, very low dimensional. So for example, for affine transformation is 6 dimensional, you still can find sufficiently small affine transformations that fool your classifier again. So really, I think that the main takeaway from all this part here is that everything that you try works for fooling your classifier. Okay, so every kind of like sensible thing that you think of will actually work. Obviously, one of the challenges when you actually have this formulation here is how to define this distance. Okay? The distance between identity transformation and tau, you cannot take like L2 norm or something like that, because this is, let's say, a vector of size 6 that have the parameters of rotation, translation, scaling, and so on. And this is the identity transformation. Obviously, taking the L2 norm wouldn't make much sense, because you really want to take into account the visual perception of the difference between the image when you apply the tau transformation and the image when you don't apply any transformation. So the transformation set is generally a manifold. It's not going to be a subspace, but it's going to be a manifold in this linear space of images, where each point here is basically a transformed image by some tau. Okay? So what we use as a distance is actually the geodesic distance from here, the original image, for example, to the minimal image that goes out beyond your classification region again. Okay? So that's, I mean, I won't go into really technical details of what is a geodesic distance and so on, but you can think of it basically as the minimal distance that you need in order to go from T1 to an image that goes outside the classification region, while remaining basically on the manifold. Okay?
What does it mean X squared?
Sorry?
X squared, what does it mean?
Oh, L square is the space of all square differentiable images, basically. So you can think of this manifold as a manifold that is embedded basically in the space of all square differentiable functions.
Then the metric depends on the space.
Yes, exactly. Yeah, we take actually the metric from this space. So the metric is really going to be the distance, like between like you need to define basically an infinitesimal metric, and this metric is going to be really the distance between two images in terms of their L2 distance, for example. So we're going to take the distance in the image space and not in the transformation space, and that's really the key thing. So here, remember that the thing I was talking about is to take a distance between the transformation identity and transformation tau. But this doesn't make much sense. So instead, what we're going to do is that we're going to take the distance in the image space itself. Again, so if you apply this with, for example, the T to be the similarity transformation, you get here kind of like a simple transformation that fools your classifier. Here it's a big transformation, but still, like, we should be able to handle this if we are sufficiently good. And with affine transformation, which is a bigger set than similarity transformation, you're able to find even smaller transformations. Okay, so far I actually showed examples on classification tasks. Now I want to really emphasize on the fact that this breaking of machine learning systems is not something that is specific to classifiers. Instead, you can actually apply it to RL agents, for example, to agents that do navigation tasks. So let's say that you have a task to code basically an agent that does some navigation on a maze. Okay? So you have a starting position and then you have an ending position, and your goal basically is to go to the ending position from the starting position. You have 5 minutes, for example, and the goal is to basically maximize the number of trips to the end position from the start position. Okay. Now, obviously, in the beginning, your agent, because he doesn't know the maze, and he only sees first-person views like this. He doesn't see it from top. Obviously, in the beginning, it's going to be to do some random walk and so on. And when, if it uses correctly its memory, then it's basically going to be more and more efficient when you do your second, third, fourth trip and so on. Okay? And the more you do trips to your final goal, the better you are, the more score you get. Okay? So this task is not a classification task, obviously. It's a much more complex task, and you'll see this more in the next lecture. But the goal here of this slide is basically to show that you can still find sort of adversarial perturbations that fool, again, the agent. Okay, so what does this mean? So the agent that was trained here works extremely well for random mazes. Okay? But now, what you can do is basically to do some sort of optimization approach, which I won't go in detail into, but you can basically find some mazes, very simple mazes to humans, in such a way that the agent just gets blocked, or like just bugs in such a way that it starts moving circles, for example, and doesn't reach its destination at all. So this is one example of such maze, which is quite simple. So if we are to do this task, so let me start from this one. So this is a human that plays the same game, and this is the trajectory of the human. Obviously, the human doesn't see the map from above again, it sees just the first person trajectory. So what the human does is really something simple. That is, like it does something like this, and then it reaches its destination. Now, what the agent does is this miss. Okay, it does this miss, and it very, very, very rarely reaches its destination. Even though there is really nothing, at least to humans, very, very complex about this maze here. Okay. Now you can't really use the same kind of optimization techniques I was talking about because it's now becoming a discrete optimization problem. You really need to start from some maze and then change it in such a way to have an agent that basically goes in circles, for example, or that just some bugs at some point. But again, the optimization technique is very simple, and that's why I'm really saying that fooling agents and fooling classifiers is really a simple task. You don't really need to get something very complex in order to do this. You just need some gradient descent approach and here's some genetic algorithm or something like that in order to solve this or to fool the agent. Okay? So as I was saying, the main takeaway is that unfortunately deep neural networks are extremely vulnerable to perturbations when you actually try to find them, when you try to optimize for them, and very simple techniques work in order to fool your classifier. Now the second question is, or the second part is going to be, okay, so I know this now, what can I do about it, right? So in the beginning, when this was basically revealed that deep neural networks are extremely vulnerable, people were thinking, okay, this is pretty easy. I'm just going to do something simple and then solve this problem, right? But unfortunately, it's been going for many years now, and there's no proper way of doing it, or there's no way of increasing significantly, really to 100%, for example, the robustness of classifiers and of agents to perturbations. So the reason why this takes so long is that actually designing defenses is an extremely hard task, unlike the task of fooling. So as I said, the task of fooling is easy, but the task of designing defense is actually very hard. And the reason why it's hard is that we're really trying to defend against all possible attacks, and not just one attack. Okay, so you don't know beforehand what is the attacker going to add as a perturbation, what is the attacker going to use as an algorithm in order to fool your classifier or your agent or something like that. Okay? So one very important thing when you actually design a defense is that you should not leverage the difficulty in optimizing the perturbations. So remember that the optimization problem that is used in order to find this adversarial perturbation is a difficult optimization problem, so we use some heuristics. So you should not really think that, okay, the attacker is not going to be able to solve this task or this perturbation very well, so I'm going to leverage the fact that the optimization itself is difficult. You really need to think that the attacker is someone that is very smart and that is going to design an algorithm in order to find perturbations in an optimal way. Okay? So we don't want to use the optimization difficulty as a proxy to define basically to design defenses. Okay? So the reason why it took so long is that people have proposed so many defenses, but these defenses again are very specific to one attack, for example. Okay? But if you change the attack, you can actually still fool the model. So in this way, you're not actually designing proper defenses, but you're designing defenses against a specific attack. And this is really not something that is very interesting at all. Okay? We really need to assume that the attacker is going to be very smart with his attack. So what we say in this community is that such defenses, which actually I don't even call defenses, that really are specific to one attack, they just obfuscate the model. So they make it harder to optimize for, but they don't really solve the problem of making your classifier robust to adversarial perturbation. Let me give you an example of one obfuscation, for example. Yeah, so let me draw here. x here, okay? This is my loss. Okay. This is 0. So the loss is 0 at the current data point x, okay? And then starting from some threshold, this t for example, the data point, so that's basically the image space if you want. That's the one-dimensional image space. So starting from some threshold here, this is going to be misclassified, right? When the loss gets too large, then at some point it gets misclassified, correct? So this is basically the threshold after which things become misclassified, okay? So this is basically x prime, okay? And x prime is of different class than x. So the adversarial perturbation is going to be this one, right? So this R is going to be x minus x prime, okay? Okay, so that's basically the robustness of adversarial perturbation of this specific classifier. Now, what I can do, to obfuscate my model, basically to have this classifier instead. Okay? Okay. So here, this classifier. Okay. So it is exactly the same. It has exactly the same robustness of adversarial perturbation because the distance you need to go in order to find adversarial perturbation is exactly the same. Yeah, it should be here. Sorry. Okay. Yet, if you actually use gradient-based methods, this is not going to change anything because if you start from x, you're just not going to do any changes because the gradient is 0. Okay. So this is a classic, like this thing in green is a not so robust model. It has actually the same robustness exactly as the black one. Yet, if you use gradient-based methods in order to find adversarial perturbation, you're going to say that this green one is actually very robust, whereas it's not. So you really need to be more more diligent in using much more sophisticated non-gradient-based methods in order to find basically adversarial perturbations for the green one. Okay? So this is what we call obfuscation, in the sense that you start from a classifier and then you go to another classifier, another loss function here, and you just obfuscate, but you don't change anything about the robustness. Is that clear? Okay, so now the community was really aware of this, or made itself aware of this, like maybe 1 year ago or something like that, because there's been like maybe hundreds of defenses that have been proposed, but none really worked well. And this was really highlighted by the 2 papers in ICML 2018 that took basically 7 or 8 defenses, like some representative defenses, and broke them all by basically changing the attack mechanism. Okay? And by saying that there is really an urge in the community to design defenses that are real defenses, and to really, when you propose a defense, you assess it against attacks that are very, like you try your best in order to design attacks that really break your model. You just don't run into the traditional algorithm and then you say, oh, look, this is actually robust, so I'm just going to publish a paper. You should really try to break your model before publishing a paper. And since then, there's really like many different papers that take previous papers, like defenses, and break them. And now there's this back and forth between like proposing a defense, and then other people show that this defense is actually broken, and then proposing other defenses, and then showing again that it's broken, and so on. So it's like this back and forth between between attacks and defenses, which is actually taking place currently in the community.
So,
Yeah.
I'm wondering which criteria should be based on to study what of behavior between adversarial attacks and anti-spoofing algorithms.
I'm not sure I got the question.
In which criteria should be based on to study the behavior between adversarial attacks and anti-spoofing algorithms?
So what do you mean by anti-spoofing algorithm?
Algorithm, the in-classifier that tries to defend the adversarial attacks.
So what is the procedure basically if we want to really like design defenses? What's the
No, I mean criteria which let's say should be based on the size of the image, or for example, adding data augmentation criteria or something like that.
So data augmentation doesn't really improve your robustness. It doesn't make you more robust to adversarial attacks, because when you do data augmentation, you generally do some random transformations or something like that, and this doesn't yield you any robustness against this kind of attack that we're considering, which is really worst case attacks. Now, the procedure you actually need to do in order to make sure that your defense is an actual defense is that you really need to work very hard to design a defense that is specific to this attack that you consider, because you are the best person to know what kind of defenses can fool what kind of attacks can fool your defense. When you propose a defense, you basically know exactly the details of this defense, and so you're the best person to basically design an attack to try it against an attack that is specific to this defense. And this is really something that should be done in most papers. But unfortunately, like there is this need to publish and so on, so there's been this like people don't do it much, but now it's actually much better. So so now there is like I gave the global picture here, but there is really one defense that stands out of all the defenses, which is really the simplest defense you can think of, which is adversarial training. Okay, and adversarial training is really simple, as I said. So what you do is basically you add adversarial perturbations in an online way. Okay, so remember that what you were doing before, if you want to train a classifier or a deep neural network, you basically backpropagate on the image batches. You consider batches and then you backpropagate this and then and so on and so forth, right? So what you're going to do instead of doing this is basically that you're going to compute adversarial perturbations in an online way for each step of your optimization. So you're going to consider this batch X here, and then you're going to add adversarial perturbations to X for the current model. Okay, so for the current network, okay, you're going to compute adversarial perturbations, and then you're going to form this new batch X plus R. Okay, and then you're going to train. Okay, you're going to compute the gradient of the network with respect to the weights evaluated at this. You're going to update the weights. And then you're going to compute adversarial perturbations again for the new network, okay? You're going to form the new batch, you're going to train, and so on and so forth. So it's an online procedure, and it basically consists in computing adversarial perturbations for the current model, add these perturbations to the data, train your model for one step, compute new perturbations for the new model, and so on and so forth, okay? So the fact that it's an online thing, that you compute adversarial perturbations for each step, is really something fundamental. It's like you cannot like use another model or something like that, pre-compute adversarial perturbations, and then expect for it to work. You really need to do it like for each step of your optimization for the current network. Mm-hmm. Yeah, I mean, that's why it's actually much more expensive than normal training, this approach. You have to really solve an optimization, because this is really exploding an optimization problem, right? So you really need to solve an optimization problem for this. So that's why it takes a lot of time. Now, the thing is that people have shown that if you actually don't solve this one very well, if you do just a few iterations, it doesn't work. You really need to solve this thing to close optimality. So that's even like even worse, in the sense that you really need to do many different iterations in order to find a good adversarial perturbation. It's not sufficient to find just one, or like one big. You really have to find the close to minimal one in order to make your network more robust. So this approach, if you consider the adversarial accuracy, which is really the number of data points that are misclassified when you add adversarial perturbation. So for a normal network, on CFAR10, for example, it's 0%, so you can basically fool everything. After you do adversarial training, you get around 50%. Okay? which is not great, by the way. It's just an improvement over this, and it's a real improvement. Nobody has been able to decrease basically this percentage here. Okay? Is adversarial training clear? Because really that's the main like algorithm nowadays that's used. Yes.
Do we do the moment training with the moment Z followed by adversarial training?
No. You just start with adversarial training. Yeah.
Does this change? Does this change the performance with the moment?
Yes, it does. And it actually, the performance decreases. So you go from like 95%, so 95% is roughly the accuracy you can get on CFAR 10, you get to 88% or something like that. So you do get a decrease in nominal accuracy, but you do get an improvement in robustness. And there is really like this trade-off between nominal accuracy and robustness. Okay, so now let's actually try to have a look what is adversarial training actually doing. Okay, let's try to understand a bit what it's doing. This procedure, online procedure of adding adversarial characteristics to your data. So in order to do this, the thing I like the most is basically to plot decision boundaries in two-dimensional place. Obviously, the decision boundaries live in this very high-dimensional space, in the input space. But we can plot cross-sections, right? So I plot basically cross-sections along two dimensions. One is a random direction, and one is an adversarial direction. Okay? For true deep neural networks. Okay? And this is what I get for normal training, and this is what I get for adversarial training. So this point here in the middle is the data point. Okay? And this is basically the decision boundary. This is class 1, this is class 2, for example. This is before adversarial training, and this is after adversarial training. Okay? So the first thing we see here is that the distance from this point to the decision boundary has increased after adversarial training, which is really something that we are happy with because that's our final goal, right? We want to improve the robustness of adversarial perturbation. So that's good. But the other thing that we see also is that the decision boundary is much flatter here. In other words, the curvature is actually much smaller in the adversarially trained network compared to the normally trained network. Okay? And yes, so the decision boundaries are much flatter. Now we can actually, like working mathematically with decision boundaries is a quite complicated topic. So it's a quite complicated like quantity. So instead of working with the decision boundary, we're going to work instead with the loss function, which we really saw during the summer school, which is really the cross entropy loss between the output of the network and the label. Okay, so we can plot basically the negative of the loss function. That's again among the two directions that I talked about, the random direction and the adversarial direction. We can basically plot the negative of the loss function, and this is what we get before adversarial training, and that's what you get after adversarial training. So again, what you get here is that after adversarial training, the loss function is much more linear than before adversarial training. Okay. Yes?
Is adversarial training could it improve the generalization of the model?
So the generalization of the model is actually roughly the same before and after adversarial training, in the sense that when you do the difference between training and tests, and before and after adversarial training, it's actually roughly the same. So what we're after really is something different. It's like the robustness to things that are outside the distribution. So you can also track, basically the loss function throughout training. So that's basically before adversarial training. So you start from a network. Okay, so that's the loss function again. Okay, and you start from a. Okay, so the first frame basically was before adversarial training. Okay, and then as you see, as you do some adversarial training steps, you get basically loss functions that are much more smooth. Okay. Okay, so now this is some qualitative experiments, but we also wanted to see this in a quantitative way. So what you can do is basically to measure the curvature of this loss function with respect to the inputs again. Okay, so that's very important. We're really studying things with respect to the inputs and not with respect to the weights. So the Hessian basically has information about the curvature of the loss function with respect to the inputs, and we can therefore plot the eigenvalues of the Hessian for a task like CFAR10. So you have as many eigenvalues as you have pixels. And this is basically the curvature profile, so basically the sorted eigenvalues before adversarial training. Okay? So you see here that there are some positive curvature, some negative curvature, and most of them are actually quite flat. Okay? That's before adversarial training. Now, after adversarial training, the curvature has significantly decreased, okay? Which really supports the qualitative experiments that we've done before, that the loss function has become more linear. Okay. Okay, I'm just going to say very quickly. There is this very, we can actually quantify this thing more in the sense that we can derive upper and lower bounds of the minimum perturbation that you need to add to your classifier in order to fool it. It's not very hard to see actually the relation between curvature and robustness. So let's say like you have this very simple toy model in one dimension where you have this basically loss function, okay, which is linear here. And again, as I was showing here, this is the threshold after which things get misclassified. Okay, so this distance here is the robustness of adversarial perturbation. Okay, so as you make your loss function more and more curved, positively curved, what you get is basically the distance between x0 and x is going to get smaller and smaller. And hence this very simple in like a full example, this relation between high curvature and low robustness. So I just want to highlight here the relation between curvature of the loss function at x0. Yes. So this one? This one? Okay, so this one here is an experiment where we actually trained, this is a model that is trained on original samples. It's not adversarial trained. Okay? And then we did some fine-tuning steps on adversarial examples. Okay? So this is really a network that works well, but that was trained only on the original samples. No, this is the loss function. This is like loss function illustrated on 2 dimensions. Okay? Random direction and adversarial direction. The goal of this plot is really to show you that as you do adversarial steps, okay, this adversarial optimization steps, you get curvature that is decreasing. So you can basically use this very simple argument in order to prove. Obviously it's higher dimension, but you can prove basically an upper bound and a lower bound on the robustness with respect to the curvature, and you really see that you have this decreasing behavior of this robustness with respect to curvature in the sense that when you add curvature, you get basically less and less robust. So if you make your if you make the curvature smaller and smaller, you get higher robustness. Now, the thing we wanted then to test for is whether this is really the main effect that leads to improved robustness, correct? Because we've seen that adversarial training leads to this small curvature, but it's not clear that if you actually optimize to have low curvature, you'll get the benefits of adversarial training. In other words, is the benefit of adversarial training really relying on the fact that you have small curvature or not? Or is something more complicated than this, just a byproduct? So what we did is basically we explicitly regularized for the curvature, and if you want, like what we did is like to regularize basically the norm of the Hessian of the loss with respect to the inputs. And if you do this, now there are some like difficulty in working with the Hessian. Hessians are very large dimensional objects, so you want to use instead like estimators. So we use this estimator, and then we use basically finite difference in order to compute this HZ. Okay? And when you basically do this kind of approximations, you basically consider a regularizer. The regularizer that you obtain is basically a finite difference between gradients, basically, to have the second order expression between x plus hz and x, where z is some directions that are taken in order to approximate well this quantity here. Okay? So when you actually regularize with this quantity, so remember that this was basically the thing we've seen in the beginning. If the accuracy on the clean samples is around 95%, and the adversarial accuracy is around 0%. Okay? So with adversarial training, things like the accuracy on the clean samples was a bit lower here, but the adversarial accuracy is much higher here. And with this approach of curvature regularization, you actually get roughly the benefits of adversarial training without ever doing adversarial training. So you really just added a regularizer to say, I really want the curvature to be sufficiently small, and you get the benefits of adversarial training. So really what the goal here of what I want to present here is that what adversarial training is actually doing is just to regularize the curvature. Okay? So this complicated procedure is actually summarized by the fact that you just regularize the curvature, or at least a part of it, because we still have some discrepancy here, like 4%. But up to this discrepancy here, adversarial training is really about making the curvature of the loss function smaller. Okay? So this is probably a regularizer that one wants to add if your goal is to achieve a robustness to adversarial perturbations. So okay, so now I just want to quickly go through the last part of the talk, which is trying to understand a bit why is it that like the robustness of adversarial perturbation is something that is very hard to achieve. So remember that even adversarial training is just achieving 50%. Okay? So it's not something great. So it's just something that is an improvement over the baseline that we have, but it's not something that is like super. So one way of actually trying to understand robustness to adversarial perturbation is to exhibit upper bounds. Okay, so what you'll see here are upper bounds on the robustness. So like you cannot achieve a robustness that is bigger than this. And so in order to achieve, like if we want to have useful upper bounds, we really need to relate them to quantities that we have a better understanding of. So we see, for example, bound with respect to robustness to random noise, which we understand better. But before going to like a bound, I just want to highlight some intuition. So consider here a very simple classification task where the goal is basically to recognize between images that have vertical stripes and images that have horizontal stripes. Okay? So that's class 1 and that's class 2. Okay? Now, there is like a second thing, like a thing that, another thing that differentiates images of class 1 and images of class 2, which is the fact that I've added a positive bias here to images of class 1 and a negative bias to images of class 2. Okay? So in other words, like this stripe here has pixels A plus A, like the value of these pixels is A plus A, where A is very small, this bias that I was talking about. And this is A, while this is 1 minus A, and here it's minus A. Okay? So there are really two things that separate these two classes. It's the fact that one is vertical and the other is horizontal. And the other thing is that they added a very small bias to all the pixels here and a very small negative bias to all the pixels. Okay? So obviously when you look at it, you don't really see the bias, right? I mean, here I just made it bigger so that you see it, because you see this difference between the colors. But obviously the thing that you really notice if you are to classify between these two classes is really the orientation of the stripe. Now let's look at different classifiers. So if you actually consider a linear classifier, this very simple linear classifier, which basically sums up all the different pixels, then this classifier is perfect in terms of accuracy, but it is not robust at all. The reason why it's not robust at all is that it picks up the bias and it doesn't pick up the orientation. Actually, linear classifiers cannot pick up the orientation. There is no linear classifier that picks up the orientation concept between the two classes. The only thing it can do, linear classifiers, if you want to achieve good accuracy, is to pick up the bias differences. Okay? So this is basically, in other words, this is basically the maximal robustness that you can ever achieve using a linear classifier. Okay? Now, on the other hand, if you consider a slightly more complex classifier, which is a quadratic classifier, you can actually pick up the orientation. And in this case, like this is just a 4-dimensional example, so it's like a 2x2 image. This is basically the formula of the classifier, of the quadratic classifier. Then you can again achieve a zero risk, or like a zero loss, okay? Like perfect classification, and you achieve actually a very good robustness. Okay? So notice the difference between these two things here. This is a linear classifier. Both of them, this is a quadratic classifier. Both of them achieve zero risk. In other words, both of them solve the task perfectly. Yet this one, with the class of linear classifiers, you cannot achieve a robustness to adversarial perturbation that is larger than this. So A here is the bias. It can be made as small as you want. Okay, so really, like if you choose A that is small, then this thing is really, really small. Whereas this one here doesn't depend on A because it just picks up the orientation. Okay? So what we say here is that there is a weak concept and a strong concept between these two classes. The weak concept is the bias, and the strong concept is the orientation. And the reason why this one is much more robust than this one is that this one really picks up the strong concept, while this one picks up the weak concept. Okay? Yeah, so this you can see it visually also. Like if you want to perturb your original data point here to misclassify it, you need to add a very small bias on top of it to basically misclassify it. While if you want to misclassify it with a quadratic one, you really need to change the orientation of the stripe. So obviously the image here is going to be completely different than the original. So what we really learned from this example is that if you have a classifier that works well, it's not necessarily robust to adversarial perturbation. We've seen this linear classifier, it's not robust. And if you really want to capture the orientation, you really have to use a classifier that is flexible enough for the task. And so if we extrapolate this idea to deep neural networks, for example, the hypothesis here is that deep neural networks do achieve good accuracy, but they really capture weak concepts. In other words, they don't really capture the concepts that we do as humans. We really capture like strong concepts in such a way that like changing them would actually like if you want to change the class, you really need to change a lot of the image. Whereas here, the deep neural networks, they really capture weak concepts in the sense of linear classifiers, for example. The robustness is therefore very much related to the flexibility of the class of classifiers that you consider. So you can actually formalize this and generalize this, obviously, and show this kind of bound. So this bound basically says that the robustness to adversarial perturbation of any linear classifier is basically upper bounded by this thing. Okay? So you have two components here. The first component is what we call the distinguishability between the two classes, and the second component is the risk, or the errors, the number of errors that you actually do. So the first component here is really a separation between the two classes. So consider the example that I previously given. If you actually take the expectation over all images that are vertical and the expectation over all the images that are horizontal, then you get something that is very, very small, correct? Because you're just going to sum them up, okay? And so this quantity is going to be very, very small, okay? And therefore, this bound is going to be in general very small for classifiers that work really well, okay? Now, the important thing here is that this works for any linear classifier. So it's not like by making your algorithm smarter, by making your training smarter, something like that, you're going to get away from this bound. This is really a fundamental bound in the sense that you can never achieve a better bound than this. So you can also show this in illustrate this bound in a graph where the y-axis is the robustness and the x-axis here is the risk or the number of errors that your classifier does. So if you have a risk that is 0, then this is the bound. So this is basically the region of linear classifiers that you cannot achieve. Okay? You can never achieve this with linear classifiers. And in the example that I've just given before, we were here because the risk was 0, and then we were looking at here. And I was saying that, okay, this is something that you cannot go beyond. This was exactly this point that I was just discussing. In general, if you make your risk higher and higher, you can achieve better and better linear better and better robustness. Obviously, if you output a classifier that is constant, okay, it's really bad in terms of accuracy, but it's very good in terms of robustness. It never changes basically. It's a constant function, so obviously it's very, very good in terms of robustness, but who cares, right? It doesn't even solve the task, so we don't care. So we really want to achieve something that achieves good performance and achieves high robustness. So we really want to be here. Unfortunately, with linear classifiers, we cannot be here. And the hypothesis is that there also exists something, this is an open problem, but the hypothesis is that there exists actually something like this also for deep neural networks. Okay? Which would really explain the fact that it's really hard to go this way unless you make your deep neural network deeper or wider and very, very harder to actually train. So if you look at quadratic classifiers, you actually achieve the same kind of, you also have the same kind of fundamental upper bounds on the robustness. And the interesting thing is that this, if you compare the not achievable region of linear classifiers and not achievable region by quadratic classifiers, this one is higher in the sense that you can achieve better robustness risk trade-offs with quadratic classifiers. And this, by the way, is very much related to the robustness risk trade-off that we've seen, that whenever you make your risk smaller, then whenever you make your classifier more robust, you make your risk larger. Okay, so there's this trade-off between robustness and risk. Trade-off between robustness and accuracy. So this was the first kind of bound that I wanted to highlight. I have like 5 minutes or so to show you another kind of bound that we can derive on the robustness to adversarial perturbations. And this bound is, as I said, relates the robustness to adversarial perturbations to a thing that we understand better, which is the robustness to randomness. So remember that the robustness to adversarial perturbations is given by this thing here. So okay, so I've used k hat for all this presentation, but now I'm using f. Sorry for presentation change. So this corresponds again to this vector. Now I can define similarly robustness to random noise, which is the same thing as before, except that I'm taking random directions. Okay, and then I'm looking what is the distance I need to travel in order to basically change my classification region again. Okay, so before it was not random quantity; it was just like optimizing for the magnitude and the direction. Here I'm taking random directions and I'm just seeing how much I should go in order to fool my classifier. Okay, so this now becomes a random quantity. Before it was not random. Okay, so the kind of bounds you can prove is something like this. There is this very, very interesting relation between robustness to adversarial perturbations and robustness to random noise. Okay, so we have that robustness to adversarial perturbations behave roughly as 1 over root dimensions. So dimension here is the real number of pixels times the robustness to random noise. So what really this says is that there is a very, very large gap between robustness to adversarial perturbation and robustness to random noise if you are in high-dimensional tasks. So for example, if you consider the task of ImageNet where you have, so 1 million pixels, not ImageNet, so 1 megapixel basically, then basically there is a 1,000 factor between robustness to adversarial perturbation and robustness to random noise. And this is really something that we see in practice. If you add random noise, you're not going to fool your classifier. If you optimize for it, you're going to fool your classifier. So more interestingly, so when the data is bounded, this thing here is bounded also, and so you have this 1 over root dimension factor, or decay of the robustness to adversarial perturbations. So we really see the fact that in high dimensions, it's much more difficult to achieve robustness to adversarial perturbations. And this is something that we see also empirically, or at least that we see the expression of, or we hypothesize that we see the expression of empirically, is that when you're, when you consider, for example, tasks such as ImageNet, which are very high dimensional, you get robustness which is very small compared to things that are more low dimensional. Okay? So in high dimensions, this is really a problem in high dimensions, is that you have this 1 over root d factor that you cannot basically go beyond. So to finish my talk, I just want to highlight the proof of this, kind of like share with you the intuition of why there is this root dimension factor between robustness to adversarial perturbations and robustness to random noise for linear classifiers. And by the way, this can be also extended to classifiers with curved decision boundaries, but not too curved, like bound curvature. So the robustness to adversarial perturbation again is this distance from x to this point here. This is the decision boundary. Now, if I want to look at the robustness to random noise, then the question is how big of a ball or how big of a sphere can I actually open around x in such a way that most of the things that I sample from this sphere here is going to be classified in this region here. Okay? This is really geometrically what we mean by robustness to random noise. So there is an interesting fact in high dimensions is that most of the mass basically concentrates around the equator or a equator. Okay? So the interesting thing is that most of the mass actually is in this shaded area here, in the sense that if I sample actually from this sphere here, then most of the points that I will get are going to be in this area here. Okay? In such a way that I can open my sphere so that the radius is root dimension, so this should be a big D. So that the radius should be a root dimension times the norm of the adversarial perturbation, and this will hold. Okay? So I can really open it much bigger. I can open a sphere that is much bigger than this one, and still make sure that most of the points that I'm going to sample from the sphere are going to be in the correct classification side. This is something that is quite surprising if you've never seen such a concentration of matter on the sphere, but this is, it takes some time to kind of like understand why it works, but yeah, this is a standard result. You really can open a ball that is much bigger than this one, than the radius of like r star of x, than one with the radius of r star of x, and really make sure that all if you sample uniformly at random from the sphere, you still get data points that are on the correct side of the decision. So therefore there is this relation between robustness to adversarial perturbation and robustness to random noise. Because like the robustness to random noise is really the radius of the sphere I can open till I basically start misclassifying, right? And that's really the cutoff between misclassifying and classifying. Okay, so these are just some highlights on the mathematics of robustness. But there are more results, and if you're interested in this, please have a look at this survey paper, which is published in Signal Processing magazine. Now, I guess it's time to conclude. So the main takeaways is that there are very simple strategies to fool your classifiers. There is an adversarial, geometric, universal, really like most of the things you can think of work well to fool your classifier. And on the other hand, defending against adversarial perturbations is a hard task. And if you and the most defenses that were proposed really make your classifier robust against just a specific direction or specific algorithm. But what we really want and what we are really after is robustness against all methods. We've seen this link between adversarial training and curvature of the loss function. And that essentially they are the same. And we've also seen some upper bounds on the robustness of adversarial perturbations, but I want to highlight that this is really an open problem. This is something that is very active in the field, and we still don't have a very good understanding. Thank you very much.
Any questions?
Thank you for this
insightful presentation. My question is about the estimation of the robustness. Can we estimate the robustness of the model using a probabilistic way? By estimating
And the
probability.
robustness. So it depends on what kind of robustness you want to evaluate on. So, like you want to assess the robustness to adversarial. If you want to assess the robustness to adversarial perturbations, there is really nothing probabilistic in here. So just use like these approaches of optimization. If you want to assess the robustness to random noise, yes, you need to take into account the randomness of the direction. You have to the randomness of the direction you're evaluating against. But it's really like, yeah, so it depends on the situation. So did you mean adversarial perturbation or like random? Or?
Estimating the potency distribution, global and local robustness.
Which probability distribution?
I mean the estimation of the robustness
Yes.
would be probabilistic intuition instead of local and global robustness by estimating the probability distribution.
So when we compute the robustness, we are doing an expectation over the distribution of images, right? So this becomes a global quantity. So in some sense, we are taking into account the distribution of your data points.
If we define the probability on attacks and minimize the expectation over attacks of losses function or losses function squared, and let's assume we have the global minimum of this quantity, can the model be? Can we say that the model is robust? Can we prove that it's robust?
I think the problem here is that, as I said, like you really want to achieve robustness against all attacks. Like probabilistic guarantees are not really interesting if you want to deploy these things in the real world, because you really can expect anything from the attacker. So even if you have guarantees, like with 99% of the attacks, you're going to basically be able to defend against. Then it just might be that the guy finds 1%, right? So I think in this field we really want strong guarantees.
But the attacks, with high probability, we know that the attacks are white noise, or we know with high probability it's not that the attacks you designed.
Well, it depends, right? So if someone has some access to your model, then he will not use random noise. He will use an adversarial noise, right? So it depends on the degree at which. So what I presented here is really white box attacks, in the sense that he has full control of the model. But you can actually show that even if you don't have full access of the model, but you just can just query it, with some queries, you can actually get much better than random noise.
Thank you, Alhussein. We are trying here to defend our models to get the best robustness. So can we say that we overtrain our models? So we are looking for all the features. So we look for only few features that the model will be more robust.
So overtraining in the sense that we are looking for all the features versus looking for just the important features. Yeah. I think that the picture here should be that we are taking features that are useful for achieving good accuracy, but that are not useful for achieving good robustness. Correct? Just like the bias, the example that I gave between bias and the bias that I've added and the orientation, right? So we really need to make sure that our deep neural network doesn't pick up the bias, because it's easy, and that's the thing. So it picks up the bias. So we really need to kind of regularize it in such a way that we say, okay, you don't pick up these, but you pick up the orientation one. But this is a difficult thing, because we don't know a priori what is the features that are weak and what are the features that are strong and so on. So it's not so easy to actually implement it in your optimizer to say, okay, I want this feature and I don't want this feature and so on.
During the last few months when I'm using Google Capture Service, I have realized that they started to show some pictures with some noise for the user to figure it out. Is this noise related to the adversarial attacks?
Probably, yeah. Very probably, yeah. The noise that you have seen is probably, it's very probably not random noise, but it's very probably noise that was chosen in such a way that it basically makes sure that you're not a robot.
Maybe last question.
Well, thank you, Hussein, for your lecture. It was very interesting in a way, understanding how we could improve our networks instead of just working out with them without knowing more about their robustness. My question is a bit specific about the slide where you presented where you're using the geodetic distance. Is that because of curse of dimensionality that you're not using the L2 distance, or
So
is that any manifold learning?
yeah, so it's really not about curse of dimensionality. It's really about what we want. If it's fine for you to use the L2 distance between two images that are very far apart, like one image that is not transformed and another image that's transformed, you can use. There is no problem at all. But it just has been shown that it's much more visually. Like acceptable, exactly. That you visualize like you measure the distance between the thing that the movie basically that starts from the original data point to the last data point by seeing how it was transformed and integrating over these, than just taking the L2 distance, right? Because the L2 distance, let's say you have two images, okay. You have like an image of a circle here, I'm taking just a simple example, and then you transform it by translating it like this, right? So this is going to have the same distance as if you translate it by very, very large amount. Because obviously like the distance between the image that contains this circle and the image that contains this circle is going to have the same as the image that contains this one and this one. Whereas here you're really going to compute the integral over all these, like over this curve, and here also you're going to then you're going to get a higher distance here.
Thank you.
Simple question maybe. When you do your minimization, maybe it's equivalent to minimizing or maximizing over a graph which is infinite. So especially when you, I don't know if you know your decision boundary or not exactly, because I think it's is it the minimization works very well, or
yeah, it does. It's like, even though it's a heuristic, it does work very, very well. But I'm not sure I understood this graph part. But maybe we can take it off.
Thank you for the presentation. I have a question. Does the dropout impact the robustness of?
It doesn't improve it.
It doesn't improve it.
No, it does not improve it.
Does not. Okay. And autoencoders may improve the robustness.
So variational autoencoders are generative models. So how do you use this?
Like instead of learning exact representations like numbers, like learn distributions instead of like exact numbers.
Like the approach that Bernardino presented yesterday. So there are a few papers on using generative models to improve your robustness, and unfortunately they were amongst those ones that were broken, basically.
Okay.